For our last big concept today, we want to talk about how you can calculate the value of gamma, the activity coefficient for any ion. And the activity coefficient's value is calculated using a rather intimidating looking equation known as the Debye-Huckel equation. The Debye-Huckel equation models the size and charge of the ion in conjunction with the ionic strength to give you a value for that activity coefficient that we can plug into equilibrium constant expressions to better take into account how the ionic strength of solution will influence the concentration of various ions at equilibrium. So first we're going to go through the Debye-Hückel equation. We're going to define the terms. And the good news is that for many common ionic strengths, if you need to find the value of an activity coefficient using this equation, you don't actually need to calculate the value of gamma using this equation every time. For many ions that you're going to work with at common ionic strengths, the value of gamma has been pre-calculated and tabulated. So Harris has tables with a lot of gamma values in the book that you can just refer to if you know the ionic strength you're looking at in a specific problem. However, for less common ionic strengths, you do need to know how to use the Debye-Hückel equation to calculate gamma, because there are many ionic strengths that you could be considering as part of your work or as part of a problem in class where the value of gamma is not tabulated for that ionic strength. And at that point, it pays dividends to know how to use the equation quickly and effectively and calculate your own gamma values at any ionic strength. And we'll show you how to come up with gamma values both ways, of course. So the Debye-Hückel equation says the log of the activity coefficient gamma is equal to negative 0.51 times the charge of the ion you're interested in squared, times the square root of the ionic strength of solution mu, divided by 1 plus an alpha term, where alpha is the size of the hydrated ion, which is a value that you can find in the tables in Harris, times the square root of the ionic strength of solution, divided by 305. So notice a couple of things. First, gamma values are specific to ions. So the ionic strength of solution is something that you'll probably have to calculate before you try to figure out what the activity coefficient is. So you'll have to calculate mu separately. But if you know what ion you're dealing with, you should know the charge, and you'll be able to find the alpha value, the size of the hydrated ion, in the table. Secondly, notice that this equation returns you the log base 10 of gamma. Once you've calculated and evaluated the right-hand side of the equation, you're still going to have to undo this log function to figure out the value of gamma that you're going to need to work with. Other than that, it's kind of an intimidating looking equation, but it's actually pretty friendly to calculate. It's not too bad. And remember, this concept of alpha, the hydrated ionic radii, gets back to this idea of the hydration sphere around the ions, which include water molecules and other associated ions at specific ionic strengths. So you can think of the alpha term as the size of the hydrated ion, the size of the ion with the water hydration sphere around it. In reality, it's a little more complicated than that and doesn't break down quite so perfectly, but that's what they're trying to model in that equation, is the size of the ion with all these associated water molecules stuck to it through ion dipole interactions. At specific ionic strengths, you can just refer to a table. Harris still has these as table 8.1 in the newest edition, I believe, as a table where you can look up the value of gamma, the value of the activity coefficient for a specific ion at any ionic strength that you're interested in. And so the way you read these tables are, the ions you might be interested in are listed in the left-hand column. And ions are grouped together in rows based on how similar the hydrated size of the ion is. So if ions have the same or similar alpha values, they get grouped together in a row. So for instance, if you're interested in a +1 ion like potassium, potassium chloride, bromide, iodide, cyanide, nitrite, and nitrate all have the same alpha value. And as a result, their activity coefficients can all be determined, are all the same number at a specific ionic strength. So if you're looking for the activity coefficients for any of these ions, they all have the same alpha value, Therefore, they all have the same gamma value at the same ionic strength. And so to use this table, you identify the ion you're looking for. You can find its alpha value in picometers in the first column. And then you look for specific ionic strengths that you might need to evaluate the activity coefficient for. In the table in Harris, only ionic strengths ending in 10 or 5 are tabulated in this table. So the first column down, your ionic strength is 0.001, 1 millimolar. These are your activity coefficient values. The next column is 0.005 molar, then 0.01 molar, 0.05 molar, 0.1 molar, and so on. So these are common ionic strengths that you might be solving a problem at. However, a value for gamma at an ionic strength that's not in the table, that's where you need to use the Debye-Huckel equation and calculate the value of gamma separately. If you're working at one of these ionic strengths, the value of gamma will be in the table. And the table extends farther down. There's a separate block for +2 and -2 ions. Again, the ions are grouped together by similar alpha values, plus or minus 3 ions, and plus or minus 4 ions. So it's worth noting just some general rules about these alpha values. As your ionic strength of solution increases from 0 to 0.1 molar, the activity coefficient decreases. In a solution with an ionic strength of 0, the activity coefficient has a value of 1. That's why in general chemistry we could just write equilibrium constant expressions in terms of concentrations, not activities. As the ionic strength of solution increases, all the activity coefficients values decrease and they get farther from 1. It's also worth noting that the smaller the size of the hydrated ion, the smaller its alpha value, the more important activity effects become, which is to say the more its activity coefficient value deviates from 1 as the ionic strength increases. So for larger ions, the value of gamma, the activity coefficient, drops more slowly with ionic strength. And for smaller ions, the more important those activity effects become at higher ionic strengths. And notice also that because the hydration sphere is included with this alpha value for ion size, alpha values do not correlate with ionic radius. Just because you know the ionic radius of an ion in a chemical compound, like in sodium chloride solid, that's not the same as the size of the hydrated ion. That's not the same as the size of the ion with those hydrating water molecules around it. All right, so I want to do one example to show you how to use this table, and we're going to use, and as well as the Debye-Hückel equation, we're going to find the activity coefficient gamma for a specific ion, magnesium, +2 ion, in a solution of 3.3 millimolar magnesium nitrate. So the first thing we need to do to find our activity coefficient is determine what the ionic strength is. As usual, the ionic strength will be 1/2 times the concentration of each ion times its charge squared, and we sum them up. If we have a 3.3 millimolar solution of magnesium nitrate, this is a water-soluble salt, so when it dissolves in water, we have 1 mole of Mg2+ and 2 moles of NO3-. The concentration of magnesium 2+ is therefore 3.3 millimolar, and for nitrate, it's 6.6 millimolar. If we calculate then the ionic strength, taking the charges on the ions into account, we have 0.0033 molar times 4 plus 0.0066 molar times -1 squared. We sum that, divide by 1/2, and we find that the ionic strength of solution is 0.0099 molar. So that is so close to a value that we have archived in the table, but it's not exactly. So from here, having established the ionic strength, there are going to be 2 ways that you can get a reasonable value of the activity coefficient for magnesium 2+ in this solution, and we're going to look at both of them. So the first is to go to the table and say, well, our ionic strength is not exactly on the table, but it's awfully close to 0.01 molar. It's 0.0099 molar. So we could use the 0.01 molar column to get a very good idea of what the activity coefficient for magnesium 2+ should be. And if we're not satisfied that we're close enough, we can calculate it using the Debye-Huckel equation. So in this case, we remember that on the table, 1, 2, 3 rows into the ionic strength, that's where we find the 0.01 molar ionic strength that we're interested in. Magnesium is a 2+ ion, so it's in the second block of the table, and it's actually in the first row. The hydrated radius, the ion size for magnesium 2+, is 800 picometers. You might want to mark that down for later when we rerun this using the Debye-Huckel equation. And if we count over 1, 2, 3 columns, here's our 0.01 molar ionic strength column. According to the table, the activity coefficient for magnesium should be 0.69. So because mu is an ionic strength that's essentially included in our table, we would feel comfortable using the table to find the activity coefficient, and we would get that the activity coefficient for magnesium 2+ is 0.69. Since this ionic strength is not actually exactly in the table, it's just close to an ionic strength that is in the table, let's practice running the Debye-Huckel calculation to see how far away the answer the table gave us is from the equation's result at this ionic strength. So a lot of the hard work for doing the Debye-Huckel equation we've already done. We know the concentration of magnesium 2+, concentration of nitrate, therefore we know the ionic strength, which we said was 0.0099 molar. And having just looked at the table, hopefully you remember that the alpha value for magnesium 2+ is 800 picometers. Now at this point, we would take these values and we would plug them into the Debye-Huckel equation to first find the log of the activity coefficient gamma, where the log of gamma is equal to 0.51 times the charge on the ion squared times the square root of the ionic strength. And in the denominator, we have 1 plus the alpha value, the ion size, times the square root of the ionic strength divided by 305. So plugging in our numbers, our numerator becomes negative 0.51 times 2 squared times the square root of 0.0099. And I get that that is equal to negative 0.193531. In the denominator, we have 1 plus, well, our alpha value is 800, so our parentheses term is 800 times square root of 0.0099 divided by 305. We add that to 1, we get the denominator as 1.248835. And if we take this ratio, we get that the log of gamma is equal to negative 0.1150. To get the gamma value itself, we have to undo the base 10 log. And so the way we would do that is to say that gamma is equal to 10 to the negative 0.1550. This decimal place got away from me a little bit as I was writing this, so if you would please make the correction in front of you, this should be negative 0.1500, agreeing with our value up here, not negative 1.500. 10 to the negative 0.1500 is equal to 0.6999, which is very similar to the value that we took from the table. But we do see that the activity coefficient value, even though it was only a very small difference in ionic strength, is probably, for the purposes of accurate calculations, a little closer to 0.70 than it is to 0.69. So those are the two methods by which you can find your activity coefficient. The next thing we'll do when we come back for class on Friday is we will put all of this together and we will show you how to use activity coefficients in an equilibrium problem to better evaluate the concentration of each chemical species involved in the equilibrium. And I will see you all then.